Hello guys, this is Matt Dean with A Plus College Ready. Today we're going to talk about motion in two dimensions, and we're going to start off with a discussion of vectors and scalars. A scalar is a physical quantity or a measurement that with magnitude, size, but direction is not factored in. Examples of scalars that we'll see in physics include speed and distance. A vector, on the other hand, is a physical quantity with both magnitude and direction. Examples include velocity, displacement, acceleration. Oftentimes in physics we'll have to add vectors together. If they're in one dimension, it's very easy. So what I mean by one dimension, east-west, that's one dimension. North-south is one dimension. If they're in two dimensions, like maybe we have one vector heading toward the north and another heading toward the east, it becomes a bit more complicated. So let's look at one dimension examples first. So here's a one-dimension example. Tom walks 20 meters due east. Remember that east we usually think of as positive. So he's going 20 meters to the east, positive 20. He then turns and walks 30 meters due west. We think of west to the left as negative, so negative 30. If our two vectors are in the same dimension, which they are in this case, we simply add them together. So negative 30 plus positive 20 gives a displacement of negative 10 meters. With sig figs, we should have negative 10.0. So if they're in one dimension, you simply combine them, making sure that you use positive and negative signs when appropriate. On the other hand, if they're in more than one dimension, if they're in two dimensions, it's a little bit more difficult. Tom walks 20 meters due east and then turns and walks 30 meters due north. What is his resultant displacement? To add vectors that are in two dimensions, we're going to use what's called the triangle method of vector addition, or the tip-to-tail method. I'm usually going to call it the tip-to-tail method. We're going to find what's called the resultant. The resultant is essentially the sum of the two vectors that we're adding together. Alright, so to use this tip-to-tail method of vector addition, we're first of all going to draw in one of our vectors. I usually like to start with a horizontal one, but it doesn't matter, you can do it in either order. So I'm going to draw in 20 meters due east. Now this is called the tip-to-tail method. And the reason it's called that is to add the second vector, you come to the tip of the first vector, and you begin by drawing the tail of the second vector, making sure that you draw that vector in the right direction. So this one, that should be due north. Mine's a little crooked, but you get the idea. This one's going to be 30 meters. So now we have our two vectors drawn. And now we're going to draw in our resultant. And remember, our resultant represents our sum. To draw in the resultant, you start at the tail of the first vector, and you draw a straight line to the tip of the second vector. We're going to label that as an R. That R stands for resultant, again, sum. To find that R, we're going to use the Pythagorean theorem. We're going to say R squared equals 20 squared plus 30 squared. Let's calculate that out real quick. So 20 squared plus 30 squared. Take the square root of that, and we end up with 36.1. Now that's our magnitude, but that's not our answer, because remember, a vector requires both magnitude and direction. And typically you're going to state that direction in terms of an angle. Typically it's the smallest angle between the horizontal and your resultant. So this angle right here, we'll call it theta. And we're going to solve for it using trig. Easiest way is to use the tangent function. Remember that tangent is equal to opposite, the opposite side. The side opposite our angle is this side, 30, over adjacent. The side adjacent to our angle is this side, the 20 side. So we go 30 divided by 20. And to solve for theta, we need to take the inverse tangent. And when we do that, we get an angle of 56.3 degrees. Now that's not enough. Typically we're also going to use ordinal directions. So usually you start with a horizontal. In this case we're headed east, And to get to our resultant, we need to go toward the north. So the way we write that is we're going to say 36.1 meters, 56.3 degrees north of east. So that means start at the horizontal, start at east, and go 56.3 degrees toward the north, and you'll have your answer. So our sum here, our resultant sum, this whole thing here is the answer. That's the tip-to-tail method of vector addition. Jam? You good? You good? Okay. Okay. This process gets a little bit more complicated when your two vectors are they're not perpendicular to each other. They're not at 90 degrees to each other. So let's look at an example of how we might handle that. Tom walks 20 meters at 30 degrees north of east, and then turns and walks 30 meters at 45 degrees south of west. What is Tom's resultant displacement? Now you could use the tip-to-tail method. You could draw these vectors out to scale, and you could measure your resultant and get an answer. That's not very accurate. It's also time consuming. So we're going to use a mathematical approach, and we're going to do what's called vector resolution. Vector resolution is a process of taking a vector and splitting it into its pieces, its parts. We'll call those components. And most of the time we're going to split the vectors into a horizontal and a vertical component. Once we do that, we can add the components that are in the same dimension, and then come back together at the end and use the tip-to-tail method of vector addition to put together the components that aren't in the same dimension. So let's look at how that might work with this particular problem. Alright, so remember, what we're trying to do is combine these two vectors. We're trying to add them. Before we can do that, we first need to draw the first vector. So we're going to draw in 20 meters at 30 degrees north of east. So that might look like so. We're going to break this into components. We're going to do vector resolution. To do that, we're going to come to the tip of our vector and we're going to draw down a vertical. We're going to call this the y component and this the x component. And we're going to solve for that x and y using trig functions. So let's use sine. Sine of our 30-degree angle is equal to the side opposite that angle, y, over the hypotenuse. Calculate that out. Y equals 10 meters. And that 10 meters is headed to the north. We can also find the x component using cosine. So cosine of 30 is equal to adjacent side, x, over hypotenuse, 20. Cosine of 30 times 20 gives us an x component of 17.3 meters. And this one's headed toward the east. So now we've broken our original vector into two pieces, a northward piece and an eastward piece. And I'm going to just write those down up at the top so we don't forget what they are. 10 meters north, 17.3 meters east. Now I'm going to erase the rest of this, and we'll do the other vector the same way. So once again, we'll draw that second vector. 30 meters at 45 degrees south of west. So that would look something like this. 45-degree angle, and this line represents 30 meters of displacement. We're going to do vector resolution, so we're going to draw a vertical. This is going to be our y component. It's going to be our x component. We're going to solve for those using trig. So we're going to say the sine of 45 equals the opposite side, y, over the hypotenuse, 30. Solve that out. So the sine of 45 times 30 gives us 21.2. And this 21.2 that we just calculated is the vertical component. It's heading south. We'll calculate the x component the same way. Cosine 45 equals the adjacent side, x, over 30. We know that the cosine and sine of a 45-degree angle are the same, so our x component is also 21.2. This one is heading toward the west. So now we've taken our two vectors and we've broken them into component pieces. Now what we're going to do is to take the components that are in the same dimension and simply add them together. So from the first vector, we had a east component, and from the second vector, we had a west component. So we're going to think of east as positive, and we're going to think of west as negative. We're going to combine those. So 17.3 plus negative 21.2. And when we do that, we end up with an east-west component, combined component of negative 3.9, or 3.9 meters to the west. All right, we want to do the same thing with our north and south components. So from the first vector, we had 10 meters north. From the second vector, we had 21.2 meters south. Remember, we're going to think of south as negative, north as positive. So when we add those together, we end up with a north-south combined component of negative 11.2, or 11.2 meters south. So far we've broken our components into our vectors into components. We then combined components that were in the same dimension by straight up addition. Now these two combined components are not in the same dimension. So to get an answer, here we have to use the tip to tail method of vector addition. So we're going to take our two combined components, we're going to draw a tip to tail diagram. So we're going to go 3.9 newtons to the west, and we're going to add that to 11.2 newtons to the south. We're going to draw in our resultant from tail of the first vector to tip of the second, like so. And we're going to solve for r using the Pythagorean theorem. So r squared equals 11.2 squared plus 3.9 squared. Calculate that out. And we get a vector magnitude here of 11.9. So r equals 11.9. But remember, that's just the magnitude. We also need an angle, a direction. And also remember that the angle that we typically look for is the smallest angle between our resultant and the horizontal, which in this case would be this angle. We're going to solve for this angle, we'll call it theta, by using the tangent function. And we're going to say that tangent of that angle, theta, is equal to the opposite side, 11.2, over the adjacent side, 3.9. So we'll go 11.2 divided by 3.9. We'll take the inverse tangent, and we'll get an angle of 70.8 degrees. And this angle's direction is, if you start at west, you have to head to the south to get there. So we're going to say 11.9 meters, 70.8 degrees south of west. So again, let's sum up what we did. When you have vectors that are not at 90 degrees to each other, you first of all want to break those vectors into horizontal and vertical components. You want to combine the horizontal components with each other. You want to combine the vertical components with each other. You can just use straight up addition and subtraction for that. Once you get those components combined, you're then going to use the tip to tail method of vector addition to combine the horizontal combination with the vertical combination. You're going to end up with a vector answer, which should have both a magnitude and a direction. Alright, next we're going to look at what's called projectile motion. A projectile is any object that once projected or dropped continues in motion by its own inertia and is influenced only by the downward force of gravity. In most cases when we're dealing with projectile problems, we're going to ignore the effects of air resistance or drag. So a projectile could be a thrown ball. It could be an arrow shot through the air. The flight path that the projectile follows is known as the trajectory. And the range is the horizontal distance traveled by that projectile during its flight. We're going to deal with two main kinds of projectile problems. Projectiles that are launched horizontally and projectiles that are launched up or down at an angle with a horizontal. This first one is a horizontally launched projectile problem. So in this case, Matthew throws a ball horizontally with an initial velocity of 20 meters per second to the right from the edge of a cliff that's 50 meters tall. So whenever you can, it's always good to draw a picture. So our ball is thrown completely horizontally. It's thrown at 20 meters per second. And the height of our cliff, 50 meters. And we want to know, first of all, how long does it take the ball to reach the ground? Well, this ball is falling vertically. The time to fall determines how long it takes it to reach the ground. What I'm getting at here is that the horizontal velocity doesn't affect that. The time to fall would take the same amount of time if the ball was dropped or thrown horizontally. The horizontal motion does not affect the time to the ground. So to calculate this time, let's just think about vertical quantities. So vertical stuff. And what we know vertically is that our initial velocity vertically is 0. We threw the ball horizontally. We have a displacement vertically. This thing is falling 50 meters, so our displacement is going to be negative 50 meters. We also have an acceleration vertically. Gravity acts in the vertical direction, and the acceleration due to gravity is negative 9.1 meters per second squared. So there's several different ways we could calculate the time. Probably the easiest way would be to use a particular kinematic equation, and that one would be delta y is equal to VOT plus 1/2 AT squared. So our delta y is our vertical displacement, negative 50 meters, and that's equal to our initial vertical velocity, because we're only thinking about vertical quantities here, times time. That initial vertical velocity is 0, plus 1/2 times A, which remember is negative 9.81 meters per second squared. And we've got to multiply that by t squared. So if we solve this out for t, we end up with a time of t equals 3.19 seconds. So that's the amount of time that it takes this ball to fall vertically 50 meters. So that's our answer to part A. Second part of this problem asks us to find the range. The range is the horizontal distance traveled by the ball, and that is completely determined by the horizontal component of the velocity. In this kind of problem, there are no horizontal net forces acting on the ball. Since there are no horizontal net forces, there's no horizontal acceleration. So that means that the ball starts off with a horizontal velocity of 20 meters per second, and it continues to have that particular horizontal velocity for the entire flight. When we're calculating distances or displacements for something that's undergoing uniform velocity, our most basic equation is delta x equals vt. So delta x, the displacement, is going to equal to the horizontal velocity, 20 meters per second, times the total time that it's flying in the air, 3.19 seconds. Multiply that out, 20 times 3.19, and we end up with 63.8 meters as our range. And it's positive because it's to the right. So our answer to B, 63.8 meters. Part C wants to know the ball's resultant velocity just before it touches the ground. So like the instant before it touches. To find that resultant velocity, we need to add together the horizontal component of the velocity to the final vertical component. We don't know that vertical component yet, so we need to solve for it. So let's think vertically again for a second. So we know the initial vertical velocity, 0. This ball's moving horizontally to begin with. We know the time in the air, 3.19 seconds. And we also know the acceleration. Acceleration due to gravity. So if we want to find a final vertical velocity of v, we can use the kinematic equation v equals vo plus at. And in this case, that's going to give us v equals 0 plus a, negative 9.81, times t, 3.19 seconds. And remember, this is in meters per second squared. So if we go negative 9.81 times 3.19, we end up with a vertical component of negative 31.3. That's our vertical component of the velocity just before the ball hits the ground. Remember that this 20 meters per second is always the horizontal component. So to get the resultant velocity, we need to combine this and this together. To do that, we're going to use the tip-to-tail method of vector addition. So we're going to draw in our first vector, 20 meters, the horizontal component, meters per second. And then we're going to add in the vertical component, which is down, 31.3. We don't need to include the negative because we drew it down, meters per second. We're going to draw in our resultant from the tail of our first vector to the tip of our second. We're going to solve for r using the Pythagorean theorem. So 20 squared plus 31.3 squared. Take the square root, and we end up with 37.1. So that's the magnitude of our velocity, our resultant velocity. We might say that's the speed. But we also need a direction. And remember, the direction we want is the smallest angle between our horizontal and our resultant, this angle right here. Again, we'll call it theta. And we'll solve for it just like we have in our other problems using the tangent function. So we're going to say the tangent of theta is equal to the opposite side, 31.3, over the adjacent side of 20. So 31.3 divided by 20. Take the inverse tangent. We end up with 57.4 degrees. And this angle would be south. Actually, we're not going north, south, and east, west here, so we might say to the right and below the horizontal. So our total answer here, our sum of these vectors, we end up with a 37.1 meter per second magnitude at 57.4 degrees to the right and below the horizontal. That's our answer for part C. All right, the final problem we're going to look at today is when we launch a projectile at an angle above the ground. So in this problem, we're launching a cannonball at a 45-degree angle above the horizontal and to the right with an initial speed of 50 meters per second. First of all, we want to know what's the horizontal component, how does this change over time, and why is this true? So we're going to draw in the vector, 50 meters per second. It's at a 45-degree angle. It's going above the horizontal and to the right. So we're going to break this into components like so. Y component and X component. In this case, we're looking for the X component, the horizontal component. So we're going to use cosine. And we're going to say the cosine of 45 equals X over 50. So we're going to say the cosine of 45 times 50, and we end up with 35.4. So that's saying that this cannonball is traveling 35.4 meters per second, and its horizontal component is to the right. How does this change over time? It doesn't. Remember that during a projectile problem, there's no horizontal acceleration because there's no horizontal net force. This doesn't change over time. For the entire flight, the horizontal component is 35.4 meters per second. Now we want to find the ball's initial vertical velocity. Again, we need to find components. We need to find the vertical component this time. To find that vertical component, we'll use sine. Sine 45 equals opposite y over hypotenuse. Solve for y. Again, we get 35.4. But this vertical component is acting in the upward direction. So this is 35.4 meters per second up. And this changes over time because it accelerates. It's accelerating due to the acceleration due to gravity. So on the way up, since it starts with a positive vertical velocity but a negative vertical acceleration, it's going to slow down. Eventually it'll slow down to 0 vertical velocity, at which time the velocity will reverse. Now you'll have a negative velocity and a negative acceleration. So on the way down, this thing's going to speed up. So the next part of the problem wants to know how long does it take the ball to return to its original launch height. So in this case, we're dealing with vertical quantities. So we only need to think about the vertical stuff. So in this case, the easiest way to work a problem like this is to realize that you're starting off with an initial vertical velocity of 35.4 meters per second. Since the acceleration is vertical, and it's the same on the way up as it is on the way down, your final vertical velocity is also going to be 35.4 meters per second. But the trick is here, on the way back down, it's going downward. So it's negative 35.4. The acceleration between those 2 points, negative 9.81 meters per second square. We're trying to find the time. So looking at these pieces of information, thinking about our kinematic equations, this equation works very nicely. V equals VO plus AT. So we're trying to find time. We know that the final velocity is negative 35.4. That's equal to the initial vertical velocity, positive 35.4, plus the acceleration, negative 9.81, times time. So now let's solve that for time. When we solve that for time, we get t equals 7.22. 7.22 seconds. That's our entire time of flight. Up to the peak, back down. Next, we're asked to find the range. Remember, the range is the horizontal displacement. Remember that horizontally, a projectile has a uniform velocity for the entire problem. When we're calculating the range, the typical equation we're going to use is this one. Delta x equals vt. So delta x is going to equal the horizontal component of the velocity, 35.4 meters per second, times the time of flight, which is 7.22 seconds. So 35.4 times 7.22, we end up with a range of 256 meters. Alright, on the next part we're asked to find the maximum vertical height. And what we have to realize to find the maximum height is when the ball gets to its maximum height, its vertical velocity at that instant in time is 0. So we're going to think just vertically. Our final vertical velocity is going to be 0. Our initial vertical velocity is going to be positive 35.4. That was our initial component of that velocity. Our acceleration vertically is still negative 9.81. And we're trying to find a displacement. The easiest way to do that is to use this kinematic equation. Final velocity squared equals initial velocity squared plus 2 times a times that displacement. So in this case, it's going to be our final velocity is 0, and that's going to be equal to our initial velocity, 35.4 squared plus 2 times our acceleration times our displacement. We want to solve that out for delta y. When we solve that out, we end up with a maximum vertical height, a delta y, of 63.9 meters. Alright, the final part of this problem asks us to find the ball's resultant velocity as it reaches the launch height. Now, the resultant velocity means we need to combine our horizontal and our vertical components at that time. We already established that our horizontal component doesn't change. So our horizontal component was 35.4 meters per second to the right. So we're going to draw that first. Our vertical component at the instant the ball touches the ground is going to be the same as it was initially, which is 35.4. But in this case, it's going to be 35.4 down. We're going to draw in our resultant from tail of the first vector to tip of the second. We're going to use the Pythagorean theorem to solve for r. Alright, let's do the math. We end up with 50.1 as our magnitude. We need an angle, because this is a vector. The angle we want is the smallest angle between our horizontal and our resultant, so this angle. We'll use the tangent function to get that. So we'll say the tangent of theta is equal to opposite side, 35.4, over adjacent side, 35.4. Calculate that out. So we're going to end up taking the inverse tangent of 1, and we get 45 degrees. So our answer here is essentially 50 meters per second at 45 degrees And in this case, it's going to be to the right and below the horizontal. Notice that this resultant velocity is the same as the initial velocity, except that it's in the opposite. It's going down instead of up. So we started with 50 meters per second, 45 degrees to the right and above the horizontal, and now we're ending with essentially 50 meters per second to the right and below the horizontal at 45 degrees. All right, I want to end our discussion today with just a little bit more information about projectiles. If the launch speeds are the same, a projectile launched at a 45-degree angle above the horizontal will travel further than projectiles launched at all other angles. Also, projectiles launched at angles of theta and angles of 90 minus theta will travel the same horizontal distance or range. So that's saying that a projectile launched at, say, a 30-degree angle above the horizontal will travel horizontally the same distance as a projectile launched at 60. A projectile launched at 20 degrees above the horizontal will travel the same distance as one launched at 70 degrees above the horizontal. And again, we're assuming that the speeds are the same, the launch speeds are the same. So we're going to quickly look at a PhET demonstration. The title of this PhET demonstration is Projectile Motion, and we'll just demonstrate these two ideas that I just talked to you about. All right, so this demonstration will allow us to model shooting projectiles at different angles. So we're starting off with a 25-degree launch angle. We're going to shoot this projectile. All right, so you can see the distance that the projectile launched at 25-degree angle, at a 25-degree angle traveled. Now let's up the angle to 30 degrees. Fire this one. Notice that one has a greater range. Now we're going to up that angle to 35. Again, fire. Notice the projectile launched at 35 travels further than the one launched at 30. We're going to up to 40 degrees. Launch again. Again, notice that one goes further than the one launched at 35. We'll up the launch angle to 45. Launch again. And again, notice that goes further. Now let's go up to 50. Launch one more time. And what I hope you notice is that the projectile launched at a 50-degree angle traveled the same range as the one launched at a 40-degree angle. Now let's go to 55. And again, I hope you notice that the projectile launched at a 55-degree angle traveled the same distance as the one launched at a 35-degree angle. Let's go up to 60. So the one launched at 60 would travel the same distance as one launched at 30. Let's go down to 30. So again, notice the pair launched at 60 and 30 end up with the same range. So two things to get from this simulation. Number one, a projectile launched at a 45-degree angle will travel further than projectiles launched at any other launch angle, assuming that the initial speeds are the same. Also, a projectile launched at angle theta will travel the same range as one launched at an angle of 90 minus theta. So a projectile launched at a 30-degree angle will travel the same distance, the same range as one launched at a 60-degree angle. Hope that helps.